it okay if I
Aryan will set it up.
maybe after?
Do you know how to do it? Yeah,
No, no, no.
I don't know.
Okay. Yeah, this.
Yeah, he will do it.
स्टेपलर करती है
Yeah.
I'm very curious. Okay. Okay. This sounds interesting. What is it? Workshop 11.
Oh, I see. I see. Oh, okay, okay. Yes, yes, yes. Yeah, this is a journal article,
Yeah.
so you will have to pay. But do it in the campus. Now do it at work.
Oh, no, okay.
Inside the campus, you have, I mean, university pays for them.
Okay.
So whenever these things happen, what we should do is log in into the Morris. No, virtual machine is the best if you can, but usually everyone is not set up for that. But log in into Morris library, and then it will work.
Okay.
Yes. Yeah, maybe I should have mentioned it for those who are doing it for the first time. The journal article that was there in homework 9, if you do it from home, it might ask you to pay. That's a paid article. I mean, or you need to pay to access that article. But our university library subscribes to that. So the easiest is to come to campus and open it. That should work. If not, wherever. If you have VPN, that's good. But if otherwise, log in into library. Go to Morris Library, log in as a user, and then search for that American Journal of Physics article. That's the easiest. If you know what a VPN is, it's a good thing to do. You can access this, then that you can do that wherever you are, in whichever country you are. Then basically what it does is that it pretends as if your signal is originating from our campus. So it's a useful thing to do, but takes a little more effort to set it up. So, hello, Niranjan.
Good morning, Dr. Service.
Thanks. Okay. How was the exam? Any comments? Maybe usually what I ask is, was it reasonable? Was it what I said it would be? So probably you guys are not satisfied. That's
It was good.
I should. Oh yeah, I returned the exams, but I have to give some averages. Well, that's midterm 2. High was 97 out of 100, and average was 74. Sometimes in these situations, median is better. This is the average. The distribution was 97, 90, 87, 64. And after every exam, what I do is I do a curve. What that means is that out of all the points that you've lost, not just in midterm 2, out of all the points that you've lost until then, including homework, everything, I return back some percentage of the lost points. So I return back 25% of the points, and all of you have full points in the quiz. So if you do not have full points on the quiz, then you don't get this 25%, you get only a percentage of that. But currently at this point, I dropped a few quizzes, so all of you guys have full quiz points, so all of you get 25% of return. And then the total is, this need not match with the numbers here, but the sequence is 92 is the highest, 90, 87, 85, 83, and 80. And a natural question, I think a couple of you already asked, is there a hope to get an A even now for all of you guys? In principle, yes. So here is what I can say. If you are down here, just keep doing what you're doing. Don't do anything else. Just keep doing whatever you're doing. If you're not working for the course, that's okay. Just keep doing whatever you do. If you're somewhere around here, do a little bit more work. And if you're here, then you need to change your strategy a little, concentrate more. From what I see, most of you guys are working hard. It's probably just how much time you're giving to this. There are a lot of things happening in your own thing. So I don't think it is a matter of your abilities. It is just probably your schedule and what you guys are, what else you guys are doing. That's my impression. It shows up in the homework itself. It does. I didn't have to wait for the exam. I sort of expected this, but I mean, usually I cannot guess the number, but the distribution sort of it's only how bad or how good you guys. Does that help? So the idea is don't give up still. A lot of things happen at the end stage. I do a lot of curving and all that. So, but whatever I do for one person, I do it for everyone. That is the only. Any suggestions or questions you guys have?
If I want to be take home class or
I don't know. So now that it is hanging on the balance in a sense, maybe take home. It's just that it shouldn't hurt anyone. So I don't know. I like to make it take home by the time of final. I would like that it's already known grades, everything. So let's wait and see. There's a good chance that it will be final will take home, but then my problem will be how do I settle this?
Is this number after 0.25% increase?
Yes, this is after,
So,
this is
you
the
know-
total, everything. This is your, if today I was going to give a grade. Today I was going to give a grade, probably what I will do is. This can change, okay, don't make it, so what I will do probably is, this is A and this is, that is an A minus, right? I don't say that A plus A minus, I do it, usually it is A and B, but. This doesn't hurt, otherwise I'll have to give a B there, so I'm only improving the grade, I'm not using. That's what I might do if I were to do it today. Does that make sense? That should answer your question. If today I were to give a grade, that's what the grades are, but that doesn't mean that's what I will do. It depends, usually depends on how you perform in your homework. Until now, I'm satisfied. It seems like you're working hard, but the rest of the homeworks, I see that there is no attempt or there is no seriousness in there. Then I have to do something. Then I'll make an exam where I'm more or I feel more comfortable giving a B like that. So I'll make an exam where your grades are representing that B. Does that help? That's how I think. Very honestly, transparently speaking, that's how I think. I would like to help, but at the same time, it's you guys who have to do it to a certain extent. Okay. Assessment is always a hard part. But that's also a job. Okay. What else? Any other questions you guys have? And you had a question? Neither. Feel free to ask if something you want to ask in my office, yeah, feel about your grades, anything, feel free to ask.
One more thing.
Yes.
Going to be the whole lecture note or just after the second
Other than,
for the final exam?
it will be full.
Or-
Yeah, it will be comprehensive final exam. It will start from the first week to the last week. Earlier, I was not doing this, whatever, I used to do this 1/3 of this semester, and then more recently, I think in the last few years, someone pointed out that even if you make one question, it helps you prepare, and that's also a way of learning. And I like that idea, so at least one question I'll ask from everywhere. It won't be an intense question, so it's just that you should be aware of what's going on. Gives you a time to summarize the whole thing in your head. So I think it's a good. Yeah, so it will be comprehensive, but of course it will be more on the what we cover from now onwards. If it is take home, probably 2 questions in the class and rest of them take home. If you've seen last year, I especially did this. Last couple of years, I've been doing that 1 or 2 question in the classroom and about 4 or 5 questions take home, which is long. Usually this is like a homework. So probably I would like to do that, but I also want to wait and see how your grades work out. And is it easy for me to just give the grades? Okay. And homework 9, there was I think Nathan, you were saying, but that is settled. Whatever article it is there, you can access it inside the app. Homework 10, I have not posted it yet, but probably by late afternoon or later in the evening, I'll post it. It will be due in a week. It's already late. 6:30. And now we have only a final exam remaining. So it's on the last day of the exam week, but the first exam and the last. Do you guys know when is your other exam? Most of how many courses are you guys taking other than me?
Just go.
Let's start with Dushmanta and Sandrika. You're taking electromagnetism other than me, right? Neither?
There is another one called special topics,
Yeah.
but there is no exam.
There is no exam. Okay. So you're also Nathan, you two, same. Okay, so all 4 of you guys are, and you guys are just okay. So do you know when the electromagnetic exam is? Then I can so find out when it is. By any, I don't think it will be on the same date because you guys have a class right after this, right? So I think the university sets it up in such a way that they are followed. So it should be fine. We will have it at that same time. Yeah. Any other questions? Okay, so let's today do Green's function in a formal way. So today's lecture hopefully gives you a clear idea of what Green's function is. I have put in enough background here and there so that whatever we need today is available for us. So let me call this Green's function. And we can also say it is forced harmonic oscillator. That's the specific particular problem we will deal with instead of dealing with a general arbitrary system. So let's also call this forced harmonic oscillator. So again, that's for specificity, so I stretch this. That's your x equal to 0, I stretch this a bit. And there is a force minus kx from the stretch, and I'm also exerting a force F, which is a function of time, and it's positive to the all right, is let's say frictionless, right? No drag, and no friction. That's just to simplify the problem. And as far as physics goes, we are all familiar with what happens. If there was no forcing, there is a natural frequency which is k over m. This is mass m, and omega squared is k over m. That means to say that if I were to stretch this and leave it, this will oscillate with a frequency omega naught. So this is omega naught will be called a natural frequency. Standard nomenclature. And now, if there is a forcing applied to it, in principle, I can use any function to represent that. But if you were to use a mono, like only one frequency you're oscillating with, and if you oscillate with the natural frequency omega naught, then we have what is called resonance. That means it could go all the way to infinity. Its amplitude can go all the way to infinity. In the absence of friction, it can go all the way to infinity. If there was friction and drag, it doesn't go to infinity. It is it's finite, and that's what in reality. Yeah. And that's what we would like to capture. But again, remember that here my idea is not to do the physics part of it, just to solve an inhomogeneous differential equation. So our equations of our mass times acceleration is equal to minus kx, and this time that is a forcing f of t divided out by a, and we have second derivative of x with respect to square. Take it to the left hand side, we have omega naught squared times x. This is equal to f of t over m. I do just for my own notation sake, just to match it with the notes I have. We have I put in a minus sign on both sides, and then let me define a of t as minus f of t over m. Like this is the only thing that may not be very natural. It could have been plus, that could have been nicer, but that's how I define it. So our differential equation is square plus omega naught square. So that's all the physics construction. Give a physical meaning to what we are talking about, and then we have a of t. So this is a forcing term. But actually, this is a given, and what we are asking for is x. I also need to give some initial conditions plus initial condition, and initial condition will be x of 0. Let's say it is x naught and x dot of 0. So the v of velocity is equal to v naught. Remember, velocity as a function of time. This is nothing but dx by dt, and sometimes we will also represent this by x dot. That's your differential equation. This is called an inhomogeneous, or I wanted to check this before I come. Is it called inhomogeneous or non-homogeneous? Non-homogeneous, that's what you're familiar with? Both is okay? Yeah. Quiz, check out what it is. Quiz, is it inhomogeneous or not? homogeneous. In my notes, it was non-homogeneous, so it probably is. This differential equation. Often you say this is a source. And that's of course what you're interested in. You're interested in solving for x of t. Immediately, you know that there is a homogeneous, corresponding homogeneous differential equation. And this one, let's call it x naught. That notation here, and plus 0 equal to x naught 0. I think it should not matter what my initial conditions are here. This can be independent of the differential equation itself, but I'm keeping it the same. And this will be homogeneous. And in this particular case, we know the solution. We have done this before, just for reminding ourselves x of t, and you did homework on this. This is a cosine omega t plus a sine omega t. So a cosine omega t plus b sine, it could be exponential also, a combination of that, all that is okay. And if I use my initial condition, it comes out to be x naught cosine omega naught t plus v naught over omega naught. See, that's your oh, that's not x, that's x naught. This is x naught. That's a homogeneous equation. And our goal is to find this. Often this could be any function that is provided and you want to solve for it. So there is a general statement you make to begin with, and let's say that's called a particular solution. By particular solution, I mean a solution that satisfies this. So x1t is equal to a of t. So basically, it is a solution. If I know x1t, I'm done. I know the solution completely, and I can go home. But then you will see that, oh, if that is true, if x1 satisfies this equation, which is our main differential equation, you will notice so if x1 t is a solution, then x0 of t, so x of t, let's say, is equal to x0 of t plus x1t is also a solution. Right? Why is that? So let's maybe let's have a symbol here, but for simplicity, the L is minus, is visible, plus omega naught squared. That's just an operator I created. So what we are saying is that L of x naught is equal to 0. L of x1 is equal to a. Then I immediately know that if I add these two quantities, I know that L of x naught plus L of x1 is equal to a, but L of x, x naught plus x1 is equal to a. That implies that x equal to x naught plus x1 is a solution. So if that is the case, is x1 unique at all? Right, so let's go back and if x1 and x2 is a solution. So that what that means is that let me say if x1 and x2 are a particular solution. This is a technical name, okay? So particular solution differential equation is a technical name for these solutions. Are particular solutions. Then we know that L of x1 is equal to A, L of x2 is equal to A. That's what is given because x1 and x2 are particular solution. And then I immediately know that L of x1 minus of L of x2 is equal to 0 because I subtract those two equations this time. And it means that L of x1 minus x2 is equal to 0. And that immediately tells me that x1 and x1 minus x2 is a solution to homogeneous differential equation. So what that means is that if, so notice this is an important realization. So a concept, I mean this will play an important role in the whole of Green's function in the construction. If x1 and x2 are particular solutions, then they are of by a term which satisfies the homogeneous differential equation. And that's the key, that arbitrariness in the homogeneous differential equation is decided by your initial conditions, which are, let's say, which are fixed, or let's say the arbitrariness of which is satisfied, and this arbitrariness is fixed by initial conditions. It's pretty much like saying when we are doing integration, like if there is a differentiation and you get an integration, that is an integration constant. And that arbitrariness can come from various places. It could come from the limits, it could come from because there is a constant you can multiply. However you think of it, eventually it is off by a homogeneous term, which is fixed by initial conditions. Once you fix the initial condition, there should be no arbitrariness. All this we are talking about x1 minus x2 is arbitrary, it's not unique. All that is until you use your initial condition. The moment you put in your initial condition, everything is gone. So there will be a lot of sometimes when you're reading on Green's function, you will see a lot of confusions associated with that. But remember that the moment you put in initial conditions, that will be gone. So that will play an important role. Okay. So that's all differential equation, but I haven't told you how to find the solution, right? So notice if I find one particular solution, I'm good. So the goal comes down to one particular solution, and that's where Green's function comes in. So Green's function is a way to find that one particular solution. So let's do this. So let me keep this intact. So idea is, this is your source, right? So the source is A of T, right? That's here. So let's break that source into many pieces. Think of electrodynamics. Charge density is a source of electric field, but charge density is built out of charges, point charges, right? Imagine, this is analogy maybe. A of T is charge density. Which means that you want to say rho of X. This is a time dependent quantity. Take A to rho and X to T. And in this case, whatever point charge is, right? Point charge is Q times delta of X minus X prime, let's say. Right. This is a point charge. And here, this will be delta of T minus prime. So what does that mean? How do I want to see this? I want to show that, I want to write A of T is equal to an integral over all time variables. So I have to integrate on something to get A of T, and for that I use T minus T prime equal to A of T prime. Again, what would you do in this case, if this is point charge? So you would say that rho of X is equal to X. Rho of X is equal to X prime plus infinity, and potentially fine. And yeah, you just want to write it like this. So basically, think of charge density. You infinitely break this into tiny infinitesimal charge components, and the tiny infinitesimally tiny region of space having a charge dq is interpreted as a point charge. So that's the idea. So any function can be thought of as built out of points. So what I'm if you really want to visualize this, so this is T, that's your A of T, and that could be your function. This is really built out of these points. At each point, there is a weight, right? How big is this line tells you how big the point charge is. So it is built out of points that you that contributes to that function, and you are breaking that using delta function. That's what we are doing. So how do we want to do this? So now you create the Green's function. Now eventually you write your differential equation for Green's function. Remember again, Green's function was not even in picture. This was our equation. But I say that I'm not going to solve this equation. Instead, I'm going to solve for differential equation for a particular source. And call this the Green's function G T comma T prime is equal to a delta function. A delta function at T prime, right? So if you want This is T prime. So in this whole T, there exists a T prime, and it has a contribution. The weighted by the value of the function A. You know that if you integrate on the right hand side, you get this complete source. So if I can do this for one source and then add them all up, I get my complete solution. What do we do in electrostatics? You find the electric potential due to a point charge, and then you add them all together, which is called the superposition principle, and get the total electric potential. And once you have the total electric potential, you can get the total electric field. That's the idea. Same thing here. Instead of doing this for a general source, you will do this for a point source, and then add up all those point sources to give you the total solution. That's the key. And that's your Green's function. And now notice, what about the initial conditions? We made a big point about the initial conditions. How does this penetrate into that? For now, I'm not going to carry on the initial conditions at all. That's how techniques that you will see in the literature will change. That's your cleverness. You can take this into this. That's perfectly okay. But remember that I told you earlier that always it will be off by a constant or a homogeneous function. If you take the initial condition at this stage, you should be aware of that you've already used it up. You've already used your freedom at this stage. What I suggest is that don't use that freedom now. We will keep this arbitrary. That means that the solution that you will get will remain arbitrary until the end. And in the end, we will come back and use the initial conditions, and that will immediately fix it. But you can do that at any stage. You can do it at this stage also. I can bring in my initial conditions, but that will be a little unnatural in the sense it's not very clear what the Green's function initial conditions are, like with how you exactly put it. But it is possible, and it's often done, and that's perfectly okay. There is nothing wrong in introducing the initial conditions immediately in them. Okay. So plus, let's say, no initial conditions. That means there will be a lot of arbitrariness.
So does it mean this Green's function is a solution to the inhomogeneous differential equation?
This Green's function is solution to this inhomogeneous differential equation. But then I have to now tell you, if I get the Green's function, let us say I solve it, that's another problem. Suppose I solve it, how does it help me get my x then? I haven't told you that yet. So that will be a few minutes. We will, by the end of the lecture, I'll give you the relation between them. And remember that all these will be off by that arbitrariness of the inhomogeneous piece. But that we will fix using initial condition. And that that arbitrariness, there are sources more than one places where it can contribute. That's what I'm trying to stress. Did I answer your question? Simple answer is that, yeah, this will get connected with X, but I haven't told you that yet. So how does this get connected? So let's do that. So yeah, so for now, once there is no equation, so let me say there is equation 1, which is recollecting this equation on my left hand side. So that is x of t, that's equal to a of t. And there is a second equation, which is a Green's function. So whenever you have a non-homogeneous differential equation, you create a Green's function. So how do you find the connection between x and t? You sort of get an idea here that, let's see, I can multiply with maybe A of P here. Oh. Yeah, I should multiply here with A of P. Prime, let's say. And this whole equation. There are two equations. First one I'll multiply with A of P prime. And then I'm going to integrate with dt prime. Go from minus infinity to plus. The first one, I'm going to do a few things. First, I'm going to make this t to t prime. So convert my variable t to t prime, and then multiply delta function of t minus t prime, and then integrate. No, I won't multiply. I want to multiply by a of t, right? The Green's function. This term. Yes. And then I again want to do this. Let me make sure.
You multiply by G, the right hand side is not the same.
Yeah, maybe it's not. Let me check before I get confused. Yeah, the first one I want to multiply by G, and the second one I want to multiply by X, not with A. Is that maybe that's where you're getting confused? Okay, so second one I want to multiply with X. I have two equations. I can manipulate however I want to. I mean, I'm seeing some few steps ahead, so probably you guys, you know, if I've seen this before, like I think we do similar tricks when you're doing quantum mechanics. When you do probability conservation in quantum mechanics, if you work with Schrodinger equation, that's very similar tricks you use. Okay, so that's your two equations. Let's now I multiplied these. I have given you some strategy, and I want to subtract them. So we are just going to do algebra. So change t to t prime, multiply by g. As I said, integrate it with dt prime. Do the same thing on the right side, but now, sorry, second equation with x, and let's subtract these two.
You have to check that D could be.
No, here I think I don't have. Okay. And then we differentiate by parts if that's what you're thinking. What's your thing? Let's do it.
I think it should be D over D fine.
Here. No, here, right? Let's see. Maybe you're right. Or let me check. Then I'll be safer. Yeah, it doesn't, at least in my notes, I don't seem to have it, but maybe it's something. Maybe you're right. That's okay, so let's start with the second equation, how it looks. So I think you have changed the two implies. So we have minus prime infinity plus infinity and x of t prime times second derivative t of t comma t prime. Oh, there's one more catch in here which I, oh yeah, that's one ingredient. We'll do it whenever we reach it. T prime and minus of omega naught square times dt prime. Right. This, when I integrate over t prime, we write that for it's more clear. Is it readable, Niranjan?
It is hard to read.
Oh, okay, so maybe zoom in a little. Better.
A little better.
Okay.
Should be the camera angle, maybe.
Yeah. Should I move this side?
It's not that bad.
This is the last zoom, right? Oh, yeah, okay. Better?
Yeah. Thanks.
Okay. Okay, so that's your equation, and let me keep it like this. Prime x of t prime that's what we were saying, this should be t prime. That's equal to x p. Okay, and first equation, similarly, will start with, and we want to subtract that out, right? So the first equation is minus of multiply by g of t. Second derivative of t times y. And x of t prime. With me? Explicitly writing that down so that it's clear what's. That's just to get a formal solution. So. Let's. I'm wondering whether to do this now or not, so whatever you're suggesting. Yeah. Can I escape that? Subtract that, I get my solution immediately. And love it. yeah, let's listen to Aryan. And do a small change. I said here that. Not to change P to prime, let's change. Here there are two P and P prime, so I swap, right? So I swap P and P prime, so go back. And, oh, maybe in the camera also you want. So in this particular equation, the second equation, since that it is not just T going to T prime because there are two variables, right? T and T prime, so I swap. So wherever there is T, I write T prime there. And what that means here is that, so I have to switch all my T prime to T prime to T, and this remains the same. T prime and T, and that's all I suppose. With me? Like when I switch that P to T prime, the Green's function, so this also changes, right? So maybe this is more explicit, right? Sorry about that. Even though I didn't want this, I didn't listen. Okay, I think so now it's okay. So now I have two equations. I can subtract them, right? So subtract these two equations. One from the other. Let me start from the right hand side and I'll write the left hand side on the right hand side. Right? These two terms cancel out. That's the simple idea. So I have x of t minus infinity plus infinity prime t prime prime. So that's my right hand side. I subtract those two quantities. The second term in each of these equations, on the left hand side, they cancel out. Right, I think. Oh, if do they cancel out immediately? No, right? Because there is a t and a t prime. So I had to come back and there is you have to come and say that certain systems allow reciprocity, and you want to come back and show this. So only those situations where you will be able to replace the source and the observer, only then this description goes. Again, have to get a physical feel for what is this assumption mean. Think of a charge and an observer, nothing else, right? Remember, if there is anything else, like if you put a conducting surface, for example, then this is not going to work. If the whole universe, empty universe, there is a point charge, and you make an observation at R. At R prime, you keep a point charge. At R, you make an observation. And now you do the reverse. You put the charge on the R prime and the observer on R, and everything remains the same. And that has to do with the translational symmetry of the universe. If there is nothing else, if you bring in a boundary there, if you can really have, it is equivalent to saying that when you look at in your sky, if there were no stars, then we have no reference. But if there are stars, then we can make a reference that, oh, this is 5 centimeters from here. So if there is anything else, then you cannot do this. Which means to say that even if you put in a conducting surface, you cannot do this. The moment you put in a boundary, then all this changes. Then you have to redo the analysis. And sometimes in some systems, you have the reciprocity and then you can work with it. So you should be careful in how you proceed. If the reciprocity is not there, how you go across it, all that is a challenge, right? So we are going to use this in the derivation. So that's when that is used, then these two cancel out, and what we have is this is equal when I'm subtracting, this becomes positive, right? So well, minus infinity plus prime g comma prime. I want to process this a little bit. Notice here the difference is that here the derivatives are acting on x, here the derivatives are acting on g. Immediately you realize that if I do integration by parts, I can make this hit on g. But what happens when you do the integration by parts? Every integration by parts gives you a surface term. Like it acts on the boundary. And you make sure that those boundary terms are not relevant for us, or if they are relevant, how they are going to contribute. Okay, and one of the key things that I'm going to show here is that this whole right hand side, okay, is going to be equivalent to the arbitrariness I talked about. If I can show that the right hand side, first of all, is a boundary term, survives only on the boundary, it is going to be a homogeneous equation. This will satisfy this. So anyway, there was an arbitrariness to begin with, because I haven't carried on the boundary conditions on G. So until I don't put in my initial conditions, this is expected to be off. So this is not necessary, but I'll show you that. But that is the key here. This is the main solution. Right hand side is the arbitrariness in the homogeneous part anyway, the homogeneous term that comes in. So let's do this a bit more. So this is equal to x of t, that's my solution. This is my main piece that will survive. Prime e comma e prime. Here prime. I put it on the right side now. And let's start with the first one and differentiate this twice. So this is equal to plus when I plus there is a boundary term, it's minus infinity plus infinity prime. That's your boundary term. And whatever remains minus often you don't, I don't know how you do the differentiation by parts. Often what you say is that you don't write this integration, you say that this is evaluated at P1 and P2, but this is a total derivative. So that's what this means. That's a way of writing that the moment this is the total derivative, these two cancel out and this is evaluated at minus infinity and plus infinity. Just to get right. Do this again. So I've done once the derivative of parts, do the second integration by parts, derivative by parts. E prime a of e prime, and I have now two surface terms. One already it's there. Then I differentiate the second time, or integrate by parts the second time, and get the second boundary term. That's going to be
Dr. Sajesh, can you move the camera, please?
wow. Okay.
Thank you.
And when I integrate by parts, this is the derivatives. E prime times E. And after the second integration by parts, I have two derivatives coming and hitting my g, that is an x. That comes with a positive sign, this comes with a negative sign, that goes away, so that all that remains. Okay. This is equal to minus infinity just giving you a feed for this x0. Okay, after I do this, I'll show that this is plus a homogeneous solution. If that is the case, then I can drop it because I'm only interested in the particular case, and I'll show that that's what we're going to do. It's particular. Again, it's just to convince you that that's what is going on. Oh, again, we have to move the camera a bit. Little bit more. So that's your particular solution. I have to show that this is equal to a homogeneous solution. And what you want to take home eventually is that every time I have a Green's function, my main solution, or every time I have an inhomogeneous differential equation, I construct a Green's function, and the main solution is given in terms of the Green function in this form. If you are doing electrostatics, this is your electric potential due to a point charge. That's a charge density. And that's what you integrate upon. And that's all you need to do. So, unless there is this reciprocity that is not taken care of, then you have to do some extra work. Then you have to go through this whole analysis more carefully. And that's what often we do. But most of the times, you don't have to worry about that. And this is all that is. And this is your homogeneous solution. So let's look at this term. Remember, there is a up and at there are two terms here, right? One evaluated at plus infinity, the other evaluated at minus infinity. So let's take a look at the surface. Yeah. And we will do this more explicitly when we are doing this more explicitly, it will be clear what all this means. So I'm just putting it on. Surface term. Let's call that G E comma prime and derivative prime evaluated at x right minus of derivative point and remember this is evaluated
at T prime is equal to minus infinity and T prime is equal to plus infinity.
If that's your surface term that is coming in from here. This piece. Which means that I can define a function s of t comma tau, where tau will be evaluated at plus infinity and minus infinity, equal t of t prime of u of t tau. And this is then equal to s of t tau equal to plus infinity minus of s of t tau going to minus. That's what. So this is either plus infinity or minus infinity.
So let's actually do minus second derivative square of plus omega naught square of s comma t plus infinity.
Right, what that comes out to. Remember that if by any chance this comes out to be 0, then I know that it is a solution to a homogeneous differential equation. If it is a homogeneous differential equation, then it is a term I said it is arbitrary up to, so we don't have to be worried about. Okay, so the time derivative hits on immediately this t is acting only on that t out there, right? So I want to see that piece. This is second derivative of t squared plus omega naught squared times g of t comma tau. And let me now be careful. There is a square bracket here and by tau and tau. And the idea is that tau tends to infinity. And can I write the next term here? Yes. Minus of my t derivative can go all the way inside because t is independent of my tau, so it can go all the way in and p by tau, make it enter, so this becomes plus. Basically, I'm acting on this and I'm recalling that this time derivative acts only on the t. Tau is all the way to infinity. This is a second variable. I don't have to worry about that. This is nothing but the differential equation satisfied by the Green's portrait. I can use the identity, and that is delta function. This is delta function of t minus tau, where tau is all the way at infinity.
this one is minus derivative. And here is what we now I have to use if t is less than tau and greater than just plus infinity. Greater than less than plus infinity and less than or greater than minus infinity and less than plus infinity, and the fact that at the surface tau is equal to plus or
minus infinity. So this boundary terms are going all the way to plus
or minus infinity, but my
key integral, the t variable is never supposed to touch that. In that case, this delta function will always be zero, like it will never contribute.
so this is always equal to zero, so then what is it's a very fine argument. Plus or minus infinity is equal to zero. So broadly, what I have convinced you is that x of t is nothing but the Green's function, presuming we can solve this Green's function, times a of t prime. That's at least a particular solution, is a particular solution.
But particular solution is perfectly fine because whatever is the arbitrariness will be fixed by my initial conditions. So that's where the homogeneous part still contributes. So it is a particular solution, and that's all we will. A symbolic way of seeing this is so that is what we are doing is L times X is equal to A. That's how you want to look at this. And we also have L times G is equal to a delta function. Delta function, often it is convenient to think of it as one in an infinite dimensional space. What that means is that you have delta of ij, correct? This has this Kronecker delta symbol. It is equivalent to a unit in dyadic notation. So this is like a unit matrix if you think of ij as your indices, right?
This is this becomes one. But then if you're having a delta of x minus x prime,
if you want to think of this in a discrete fashion, at least have an imagination that oh, x and x prime are I and j, because okay, it can be taken to a great extent that analogy can be stretched. That also is one. In that infinite space now, this is finite space typically, right? 1, 2, 3, that three-dimensional matrix. This is now an infinite dimensional matrix. In that way, that is equal to 1. If you think like that, so what I have now told you is this x is g times a. So what that means is that here this implies that x is equal to L inverse of a, right? If I think of it as an operator, L, a differential operator acting on x gives you a. So x is L inverse of a. And what is here? What is L inverse? G actually is L inverse.
Okay, so what is the Green's function? It is the inverse of the differential operator. So x is equal to L inverse of A, symbolically speaking, that's equal to G times A, or Green's function is the inverse of differential operator L. That's what we mean, G is equal to L inverse. That's a basic idea. Again, at a differential operator level, we are not taking with any to any physical content in here. And practically speaking, this is what we will do. We can find G, and the solution is simply given by the integral of that with the appropriate initial conditions. And next time we will solve for this Green's function and find various solutions. Notice this is a particular solution. Particular solution can be off in many ways, so there will be many solutions we can find based on the way we approach. Okay, thank you.
Thank you, Dr. Sajay. See you next time.
Thank you. Bye-bye.
Bye.
Mhm. Oh. Yep. That's okay. That's all. Nice. Okay. Did you get to go to Chicago?
Oh, I went to a bunch of champagne.
Oh,
We do
okay.
short time. Oh, we gathered at a bunch and we had some fun times. We would have said that let's go to Chicago. Then if only option we had was food.
What are you guys doing there?
Just, I haven't seen the whole Chicago yet. So I have
Uh-huh.
been many times. Every time I would like to see some parts.
Yeah, it is.
Time is always short. It's just weekend.
Yeah, it's big, right?
I haven't. I read it over the.
Tell it again?
I read the article.
Okay, but do submit that also, okay?
Yeah, I did.
Oh, yeah,
I wrote it up.
yeah, that's good. Yeah.
So we have time until 4:30 submit.
Yeah.
Okay, thank you.
It take a little extra time.
Thanks.